First, a technically useful lemma. If two subspaces are independent, and the second of them is itself split into an independent family, then the whole collection taken together is independent in V. The corollary, V being the direct sum of the first two, together with the second being the direct sum of the rest, gives V as the direct sum of all of them. So direct sums can be taken apart a layer at a time. Now the projections. When V is the direct sum of a family, the map from the product to V is an isomorphism, so it has an inverse. Composing the jth coordinate projection after that inverse gives a linear map from V into the jth subspace. Since every vector is uniquely a sum with one term from each subspace, that map sends a vector to its own share in the jth1. The book calls that share the jth component, and the map the projection of V onto the jth subspace. Note that the word projection now has three different meanings in this book. The coordinate projection on a Cartesian product, the projection onto a quotient space, and this one. They are related but distinct, and context settles which is meant. The theorem, the ranges of these projections are exactly those subspaces, different ones composed to zero, and all of them sum to the identity. Those three are the reflection in V of the identities that held on the product space. The converse holds as well. If a family of maps on V sums to the identity and different ones composed to zero, then taking their ranges, V is the direct sum of those ranges and the maps are the corresponding projections. That gives projections an intrinsic characterization. They are idempotent. Each composed with itself gives itself. Equivalently, each is the identity on its own range. And the null space of one is the sum of all the other subspaces. The converse holds too. If any linear map on V is idempotent, then V is the direct sum of its range and its null space, and the map is the projection onto its range. So being idempotent and being a projection are the same thing. The proof is short. Set Q to be the identity minus P, then P composed with Q is P minus P squared, which is 0, so the previous theorem applies, and the range of Q is exactly the null space of P. A pair of maps summing to the identity whose composites both ways are 0 is called a pair of complementary projections. The book closes on a fine point. Strictly, summing those projections mismatches the codomains, and an identity injection is needed to make it exact.